We are trying to grow the repertoire of things that we know how to differentiate, things that we know how to find the derivatives of, things that we know how to determine the gradient functions of. So what I'm going to do is I want to think about what happens when you take functions and you put more than one kind of function together. There's lots of different ways that you can combine functions, just like there are lots of different ways you can combine numbers, okay? So we're going to go through them in turn. Today, actually, it's going to be a pretty simple one. It starts off simple. You'll almost think, like, what else could it be once you see this result? But part of the point is that, well, it could be other things, as you'll see when we have a look at some of the more complicated ways of combining functions, okay? So here's our first one. The derivative of a sum of functions, okay? So if I have some function f, okay? And some function, which itself is a sum, okay, of two different functions. I'm going to call them u and v, okay? U and v. Not you and me, you and v. Okay, now, let's just think about this for a second, just so you don't lose what's going on. You're used to seeing f of x, right? F of x. What this really means is, f is the name of the function, right? F is the name of the function, and x is the variable that you put into it, right? The variable that is input, okay? Now, we have been looking at functions with names that have particular variables all the time, okay? So, for example, one of the most famous ones that you guys already know is pi r squared. Now, what is the name of this function? It's the area of a circle, right? Now, usually it's kind of unambiguous that we're talking about a circle, so you'd say A for area. So A is the name of the function, capital A for area. Not an x to be seen, right? What's the variable that's input into this? It's the radius, right? So you would say A of r equals pi r squared, okay? So don't freak out, like it's just a name and it's just variables. Sometimes you even get more than one. For instance, you might recognize, just in the same neighborhood, you might recognize this. What could this be? The volume of a cylinder, right? Now, there's not just one variable that gets input into this, is there? Right? In fact, there's two. You need the radius, and you also need the height, right? So, just look at this. It's the same idea. There's the name of the function, and it just so happens that in this case, you've got more than one variable that gets input. Okay? All I want you to understand is, now when you look at this, what does this mean? Okay? This means u is the name of the function, and it also gets x's put into it. And v is another function, and also gets x's put into it. These could be anything, right? For instance, this could be like x cubed, okay? And this guy could be 2x. Or fine, okay? Anything you like, any kind of combination where all you're doing is you're adding them together, right? So, having that piece of notation up your sleeve, if this is what the function is, then what would its derivative be? Okay? Well, by definition, let's just start with the definition. The derivative of any function is the limit as h approaches 0, right? And on you go, okay? So let's just quickly put that down. As in so many other cases, and you've heard me say this before, merely writing down this formula isn't meritorious, doesn't deserve you any marks, but it does help it get in your head what you're doing, right? Rise over run, tangent not secant, and then you won't screw it up when the latest stuff, which is what you get awarded marks for, is incorrect, because you saw where it came from. Okay, now I know what f is, right? I know what f is. So instead of all of these, I can replace them with what it's really equal to, which is u plus v. You've noticed I've stopped saying u of x plus v of x because I don't need to keep on saying it. They're all functions of x. Okay, so when I say u, you know what I mean. Okay, it's u being a function. So I can say limit as h approaches 0. Okay, now what is f of x plus h? Right? Well, it's f of x, but instead of x's, everywhere you see x's, you put in x plus h. So I see an x there, and I see an x there, so I should put in x plus h. Right? So on the numerator here, I've got u of x plus h plus v of x plus h. Okay, so that little component there, those two terms have come from there. Make sense? Okay, in exactly the same way, I am going to subtract f of x. Well, I know exactly what f of x is. It's this, okay? So I could say take away and then put some big brackets around that, but I'm just going to expand the brackets, do that all in one hit. So I've got minus u of x minus v of x, okay? So you've got this part here, take away this, is just me substituting that straight in, okay? And of course, it's all divided by h, okay? Now, it only takes a slight little bit of rearrangement here, okay? Can you see I've got a u term here and a u term here, okay? And if I just ignored the fact that they were u's for a second, suppose they were like f's or g's or whatever letter you'd like, okay? X plus h, that function there, minus at x, that's just first principles, isn't it? Like it's right there, just with a different letter. So let's rearrange it to make it a little more obvious what's going on, okay? This is kind of like what you do when you rearrange a quadratic to make it easier to factorize, okay? So I've got u of x plus h here, and then take away u of x. Gather the u's. Then put the v's over here. Now, I could stop there, okay, and put it all over h, but just to make it even more obvious what's happening, I'm going to write these as two separate fractions, right? They both have the same denominator, so I'm going to make this one over h, and I'm going to make this one over h. You okay with that? Yep.
You have to add the limit of h approaches 0.
Okay, I will in a second. Yeah, I will in a second. So what have I got now? What have I got now? I have the limit as h approaches 0 of this big enormous thing here. Okay, this big enormous thing. Now, when we had a look at limits before, okay, limits are all about, well, how is this thing behaving as this happens? Okay, how is this behaving? Now just think of a simple limit. Just think about the limit as, say, x approaches 0 of, oh, I don't know, say x squared plus 1. Okay? Now this is a nice easy thing. There are no asymptotes. There are no holes in the function. Okay? So you're like, all right, here is x squared plus 1. Right? And whether you come from below or whether you come from above, you're just going straight to that value. Right? And of course the intercept is 1. Right? So you know that this is equal to 1. Okay? But you can also see this another way. Instead of just going straight there and saying, okay, what's it equal to? You can see that because I have a sum in here, right? I can kind of think of these two as two different things. I can think about, I need more space. I can think about the limit as x approaches 0 of this guy, which of course is just going to 0, right? Plus the limit as x approaches 0 of this guy. Now, this is independent of x. There's no x's in here. So it's just going to do the same thing it was doing all the time, which is go to 1. So this is 0 plus 1, 1 as we saw before. Okay. So when I have the limit of a sum, you can break this apart in exactly the same way that I broke apart this fraction. Okay. So now rather than have one limit, one big thing, I'm going to think of two limits. Limit h approaches 0 of this, plus another second limit, which is exactly the same, but with v's instead of u's. Okay, I'm pretty much there now, okay? These lines, it's a bit messy, these lines by definition are the derivative of u at some point x. This is u dash, okay? And of course this being exactly the same thing, is the derivative of v at any given point x, v dash, okay? And of course what I began with is f dash x, okay? So what have I concluded? When you are differentiating, finding the derivative of something which is a sum of the functions, right? The derivative of a sum is the sum of the derivatives. Can you say that again? Derivative of a sum, like that, is the sum of the derivatives. That's it. It's very, very simple. You're like, what else could it be? Well, as we go forward, you'll discover it can be other things, right? When we combine them not just by adding, right, but by, say, like multiplying, you like things go out the window, Okay, so I like that. It's so memorable. I'm even going to write down, encourage you to do that as well. The derivative of a sum. The derivative of a sum is
Oh my gosh.
the sum of the derivatives.
Oh.
In other words, when you're differentiating a big long thing, which is a whole bunch of terms all added together, just take them one at a time, differentiate them individually, and out it comes.